Hello everyone, and welcome to the second day of our workshop on Asia, so for the Copernicus Marine Service. My name is Gaëlle Navsterbik, and I'm a training officer at Mercator Ocean International, and I'll be your host for today. So as you know, today is the second day of the workshop, and today is the practical session using Copernicus Marine data. So before we start, we are just going to go over some house rules and guidelines to make sure you enjoy this webinar. So first, we ask you not to use the chat that you will see on your right-hand side for your questions. You can use it for small talk or to say hello to us, but if you have a more technical question or content-related question, we invite you to use the dedicated Q&A section that you will find on the top bar of your screen. So simply click on it to open the dedicated space where you can ask our speakers your questions. Okay, I think the slide is not moving forward. Oh, sorry. Okay, thanks. And next to the Q&A section, you will also find the section dedicated to the poll for the workshop. So feel free to fill it out at any point during the event. Then, concerning the agenda of today, so we will have 4 demonstrations. The first one being by Rezak from the Mercator Ocean User Support. So we will present to you the Copernicus Marine Toolbox, and then we will have the 3 tutorials that our experts from Novelties prepared for you today. And perhaps even some of you had time to practice before the session. So we will start with the Jupyter tutorial by Alexandre Merin, then the QGIS tutorial by Daria Andrievska, and finally the R tutorial by Simon Millet. So now let's dive into the first presentation, which is about the Copernicus Marine Toolbox. And welcome, Rezak, and you can start the presentation whenever you're ready.
Thank you, Gaëlle. Can you see my shares?
Yeah, we can see the slides.
Okay. So, good morning, everyone. So, for those who didn't attend my first presentation, I'm Rezak from user support team on Copernicus Marine. And today I will be presenting another tool which is used to remotely open and download Copernicus Marine data, which is the Copernicus Marine Toolbox. So the Copernicus Marine Toolbox is an open access package, a Python package used to retrieve all the metadata information related to all the data sets contained in our products. It also allows to only select and download only subset of this data by selecting only few variables that you wish to explore within certain geographical area. And the toolbox also allows us to access the original file service, which will allow to retrieve the data in their original form. Another advantage of the toolbox is that there is no quota limit memory when it comes to the memory size. Unlike when using the graphical interface, you cannot exceed the 800 megabytes. So when you use the toolbox, as long as your machine can handle the memory, then you are good to go and download all the data that you need. The toolbox also allows an optimized way to download the data. This is due to the conversion of the data to the analysis-ready cloud optimized format, the ARCO format. So that means that the data has been homogenized for ease of use and interoperability. It also means that the data is stored in clouds, which allows the fast parallel access to it. So the toolbox also allows to access various services. Among these services, we have the ARCO GeoSeries service, which is optimized to analyze large geographical area within a small period of time. It also allows to access the ARCO time series service, which is optimized to analyze small geographical area within large period of times. And we also have the original file service, which allows the access to the data in their original form. So to access the services, the toolbox provides various functions that you can use in order to remotely open and download our data. So first we have the login function. So this one allows us to log in order to get started working with our data. So it's the first function to execute after, of course, installing the toolbox. So the particularity with this one is that it allows to generate an automated file containing your credentials. So it's a one-time process, and you won't have to log in each time you need to enter our data store and download our data. We also have, sorry. We also have the describe function. So this one allows us to retrieve all the metadata information related to our data sets. So the particularity with this one is that it does not requires to be logged in. And then we have the get function. So this one allows to access the file browser service in which you will get the data in their original form. So just keep in mind that when using the get function, you will have to download the data sets with all its variables, and you won't be able to select a certain geographical area. And then we have the subset function. So the subset function allows to only select subset of data from a data set by selecting only a few variables, as I said earlier. And you can also select certain geographical area that you wish to explore. So to execute this function, you can use two different support. So you can use either the command line interface support. In this case, you can use a mini force prompt like the one I use myself. You can also use a Python API interface, application programming interface. For that, feel free to use a Jupyter notebook or VS Code to work with the toolbox. So now let's get started and show you how to get started with the toolbox. So first things first is to access our interface and go to the user corner section, and then access the help center and FAQ section here. So in here you can find various sections that speaks of each section, of course, speaks about various topic in our service. So the one that we need to access is the Copernicus Marine data download. So you click on it, and then you will be getting also some sections. Of course, each one, of course, have its own topic. The one that we need to access is the Copernicus Marine Toolbox section here. And as you can see, we have also some subsections. Of course, each part speaks about a certain aspect of the toolbox. So the first one, of course, speaks on how to get started with toolbox. We have an introduction article, which defines the toolbox and how to use it. We also have the installation articles, which is a pretty interesting one, which lists and defines all the steps and the option that you have when it comes to installing the toolbox. We also have another interesting article which allows to use the toolbox without installation. It's basically an executable file to download and start working with the toolbox. This is especially for those who don't particularly use coding coding language. So I invite you to check it if you want. And below we have the main functionalities. So here we have the various functions that you can use with the toolbox in both supports, in the command line interface as well as in the Python API interface. Use cases. So in the use cases section, we have various examples on how to use the toolbox with use cases. Of course, for those who don't wish to work with Python, we also here have some use cases on how to work with the toolbox in R and also in MATLAB. And finally, we have troubleshooting and FAQs. So here we have a pretty interesting article, of course, which is the troubleshoots article. So this one contains all the common issues that you can encounter when using the toolbox. So let's say that you have installed the toolbox and you started working with it, and then you encounter an issue or a bug or something. So it's recommended to check the troubleshoots article, because maybe you're going to find the issue that you are encountering and the solution to it as well. Reporting an issue or feature request. In here, it's listed on how to report an issue or a feature request. Next, milestones and roadmap. This article speaks about the future releases of the toolbox. Of course, to inquire more information, you can always go here to the message icon and consult the news icon, as for example, and scroll down. In here, you can find the latest version of the toolbox you can use. Of course, we always recommend installing the latest version of the toolbox using a Mamba environment. Why Mamba? Because it's the one that is optimized to use the toolbox efficiently, and it prevents to have all the errors related to conflict between dependencies. So yes, it's always recommended to check this section to make sure that you are using the latest version of the toolbox. You can also check the help icon here and go for the help in case you need some extra tips or extra information, and type in, let's say, toolbox introduction. So when you type in toolbox introduction, you're gonna get some articles related to your question, and then you're gonna find, let's say, the introduction article which I spoke about. There is also the installation articles and the services provided by the toolbox, various information that you can explore to get further information on it. And there is also a way to inquire information by going to the message icon here and ask a question to our chatbot Blue. So let's say that you need to inquire about the toolbox and say how to use the toolbox. So Blue is going to explore our data center and try to come up with the best possible answer based on the question, of course, that you have asked. And as you can see, it will provide you with option that you can explore to use the toolbox. And if you can check here in detail, you can see that each number refers to a certain reference. The reference is usually an article which will help you to explore and get further information on it. Of course, if the answer provided by Blue isn't satisfying, you can always type in, I want to talk to a human agent, and then you will be getting in touch with us, and we will be glad to assist you further. So let's say that you have followed all the necessary steps to install the toolbox, that you have created your environment and you installed the toolbox. So the next step is to begin working with it. And for that, I will access my mini force prompt to show you how you can use the various function after installing the toolbox. So the first step is to activate your created environment. For that, you can simply type in Mamba activate, the name of your environment, course. I name it latest Copernicus Marine Toolbox. Feel free to give it the name that you wish. And as you can see, I'm no longer in my base, but in my environment. And you can always check your toolbox version to make sure you are using a recent one by just typing Copernicus Marine, which is the name of our package, followed by the version option. And as you can see, I'm using the latest one, which is the 2.2. So now let's begin with the functions. So first function that we will explore is the describe function. Again, it's simple. Just type in the name of our package, Copernicus Marine, followed by the name of our function, describe in this case, and just going to print the option that you can include within this one. So for that, you can use the help option to inquire more info about it. Type in enter, and then you will be getting all the options that you can include when using the describe function. Of course, the options are in the left and the description are in the right. I'm not going to dive in detail and explain each one. So what I recommend to do is check our help center and type in describe function of the toolbox. and you'll be getting the related article which explains in detail on how to use this function. So now let's move on to the login function, which allows us, of course, to log in. So again, you can just simply type in the name of our package, Copernicus Marine, followed by the name of the function to execute, in this case, login, type in enter. And as you can see, it requires to put my credentials. So you can put your credentials and also your password. As you can see, when typing the password, make sure you are typing the right one because you won't be able to see what you are typing. So of course, I've already used this function, so it's basically telling me if I want to overwrite it. So let's say yes, just to show you the file. And if we go back to my Copernicus Marine environment, you're going to see that the file is automatically generated. So now I'm logged in and I can now use the rest of the function of the toolbox. So the next one we will use is the get function. So first we're going to print the details that you can use also within this one. And for that, just as I stated, you can use the help option, Copernicus Marine get help. And then as you can see, I have all the options here and the description. Of course, all these are optional except for the first one, which is the dataset ID. Yes, the dataset ID. You cannot download data unless you join the dataset ID that you wish to get. Of course, you can use dataset ID or simply I to short it. And now I will give it an example. Again, if you want to explore more this function, just go to Help Center, type in get function of the toolbox, and you will be getting all the information in details on this one. So now let's give it an example with get. I will try to download, so Copernicus Marine, the name of our package, followed by the function itself. And now I will specify my dataset ID. So for that, I will just going to use the dataset that I have presented in my first presentation. Just going to copy the name here. This is the dataset ID. And then I will add the filter option to specify a certain period to download. It's possible when using the get. So for that, I'm just going to download a certain period. And for that, I will use the regex option to specify the period to download. For that, I will choose, let's say, I want to download data from the 21st to the 22nd of May, 2025. 21st to the 22nd of May. Close the option here. And then I will specify also my output directory in which I wish to store my data. And for that, you can just use output directory or simply O to short it. Go back to here and copy the path to my directory and paste it. And now I'm ready to download my data. And if we check our directory, you're gonna see that the data is being downloaded. So perfect. Of course, we are just not going to wait until data is being downloaded. The most important thing that you can see that the data is indeed being downloaded in the directory that we have specified. So now to present the rest of the functions, I will switch up to the Python API interface. And in my case, I use Visual Code Studio. You can use Jupyter Notebook as if you wish so. So first things first, in this case, is to import the Copernicus Marine package. So simply type in import Copernicus Marine. So now that I've imported my Copernicus Marine package, I am ready to download my data. So for that, I'm going to use the subset function. Before, we will print some details on how to use this one and what are the options that I can include. So just type in Copernicus Marine, point the name of my function, subset in this case, followed by an interrogation point. Of course, this command is the equivalent to the help command that I've used in my Miniforce prompt terminal. So run it, and as you can see, I have all the options that I can use within the subset. So let's give it an example on how to download the data via subset. Again, just going back to my first presentation to copy the template that I have used. So of course, for those who didn't attend my first presentation, it's also it gives you a little glimpse on how to download a subset of data using the Viewer Pro and the toolbox. So for that, just go to the download icon here, and I want to download, let's say, this area that I have created. So just click on the final map option and then click on the area itself, and the information will be automatically filled. And then go to the automate option here. And now I have two different templates for subset. So I have one with the command line interface support and another with the Python API support. Of course, this is the one that I want to use since I'm using the Python API support. So simply copy it, go back to VS Code and paste it. Here, it's no need to import it again. And now I can also add another argument, which is the output directory, in which I wish to store my data. Just going to use the same one, data, copy the path like this. And now run the cell. And as you can see, the data is being downloaded. It's in progress. And yes, the data is downloaded. You can check if the data is here. And as you can see, indeed, my subset of data is downloaded. So now move on to the next function. So this one is called the open dataset function. Again, we will print some details about this one, and then I will define on how to use it. Open dataset. So the open dataset is also a function of the toolbox, which allows to remotely open our data and explore it. Of course, the difference between this one and the get and the subset is that the open dataset does not allow to download the Copernicus Marine data. However, it remains a pretty interesting function, since let's say that you want to download our data, but you don't exactly have the ID of the exact data that you wish to download. So the open data set allows you to explore all the data by remotely open it without having to download it each time and then having to repeat the process. So it's a pretty practical function which allows you to browse various data that we provide, and then select your data to download, and then proceed to download it. So as you can see, we can include also various options when using it. So let's give it an example. I'm just going to copy and paste my subset template here, since it's basically the same arguments that it takes, except for the output directory, because as I stated, when using the open dataset function, we cannot download the data. So open dataset, just give it a name here, dataset, and print it just to see our data. So now, as you can see, my data is being printed. And as you can see, I have all the details. I have the the dimensions, as well as the variables and the metadata related to my selected subset. Of course, for those who wish to export their remotely opened subset to netcdf file, it is possible to use the to-netcdf method. For that, you can just type in the name of my created subset with open dataset, followed by the to-netcdf method, and you also have to specify your output directory. For that, I'm just going to use the same one, copy the path here, output directory, and don't forget to give it a name. And in this case, I will just name it data point NC. Of course, NC stands for netcdf, and run the cell. And as you can see, my data has been exported to a netcdf file, and it is stored in my target directory. So there is a way to store, to get the data that you have remotely opened by using the to-netcdf method. Now let's move on to the next function. This one also allows us to remotely open our data, but in data frames for those who wish to work and explore the data in CSV format. You can use the read data frame function, and for that, again, it's basically the same template. So just going to copy and paste this one and rename it read data frame here, and run the cell. And my data should be opened in data frame in a few seconds. And as you can see, yes, I have all my dimensions as well as the time with my variables and the values. Of course, just keep in mind that when using this one, you have to first select your subset of data and then open it, because otherwise you will be getting some message telling you that the data that you have selected is too large. So in case you have selected too large amount of data, you can find trouble opening it. So just make sure to firstly select your data and then open it with this one. And to export this data into CSV, for those who wish to analyze the data in a CSV format, there is also a method to do it. So it's basically the same one as to netcdf, except for this one, you're just going to replace the method to CSV. Again, specify the output directory as well as the name of your file. And in this case, I want it in a CSV format, and that's it. Run the cell, and my data is exported into a CSV file. So I think that's it. We have covered all the needed parts and features that you have to get knowledge on it and to get started working with the toolbox. I hope you enjoyed this presentation, and if you have any questions, please ask them. I will be glad to answer it. And enjoy the rest of the event. And thank you, everybody.
Thanks a lot, Rezak, for your presentation. It was really interesting. And yeah, we have a few questions for you, so we will go to that part now. Actually, we have two concerning the Jupyter Hub, I think. The first one being, is there a limit to the size of the data files that can be stored on the Jupyter Hub when running a tutorial, I guess?
I think there is indeed a limit of size, but I don't exactly know what is the size of that you don't have to exceed. The users you can save the question, and I will inquire about it to answer it in details and tell it yes. You need to give it the exact answer for that. But yeah.
Okay. Oh, I put it on the side. The next question, I think probably the same person actually. So still on the Jupyter Hub, is it possible to download other Copernicus data such as ERA5 data?
ERA5 data, It's also, I would say it's not possible, but just to confirm it, I will also give it a look and yes, and get back to the user and answer it. But yes, I will give it a look and try to find to give it the exact answer. I don't want to say it's not possible, but prefer to investigate first and then I will see.
Yeah, I think we have a few data sets with error 5 data inside, but I don't know if it's like reanalysis using error 5 at some point or if it's fully error 5 data. So yeah, maybe we can check
Yes.
that. Okay, so a question concerning the open data frame function. Does it work too when you have data in isGrid?
The open data frame function is, I would say yes, because it uses tool when using the open data frame, it's practically the same as using the open data set. So all the data sets, when converted to the ARCO format, are are eligible to be used within the open data frame. So I would say yes.
Okay, okay, thanks for the explanation. Okay. Yeah, no, it's fine. Is there a way to find the dataset ID straight from the toolbox without going to the home page?
No, I would say no. Yes, you will have to go to the home page and access the data store and access the data in order to get the dataset ID. I was trying to find if there is a solution and get it with the toolbox, but yes, there is no function that allows to get the dataset ID without consulting the homepage first. So yes, it's
Yeah,
not possible.
yeah, that's what I was thinking also. Okay, I think I just have a small issue with my screen, but we can go to the next question that I can't highlight for now. Which is easier to use, VS Code or Jupyter?
That depends on which interpreter you feel comfortable with. I would say that they are both easy to use, and the difference lies in the interface and the yes and the option that you have. But yeah, VS Code or Jupyter, honestly, is the same thing. But I mean, you can use the one that you wish comfortable with, and the one that you always worked with. In my case, I use VS Code, and yeah, there are others who use Jupyter. So yeah, it's the same thing.
Okay, thanks a lot for the detail. Okay, it's back now. So the data you presented, I guess, is until 2023. Is there any sensor we can use if we want to analyze 2024 mean height wave, I would say?
Yes, of course. I just use an example just to demonstrate how to use the function. But yes, there are data that goes to 2044 to 2045. I mean, the period differs from a data set to another, from a product to another. So, in case you are interested in 2024 period, just go to our data store and select in the filter option, in the filter section, sorry, the area that interests you, and then you will have a set of products that matches the selection and the period of the products, and then you can select the one that suits the period that you wish to explore or download. So yes.
Okay, okay, thanks a lot. Up, and I think we have time for one more question. Have you implemented or developed a project using this toolbox and were the results obtained both accurate and reliable after programming? It's a general question. I guess the accuracy of the results, if you code something, doesn't depend on the toolbox. So I don't know if the
Exactly, yes. I didn't particularly develop a particular project using the toolbox. I mean, I use the toolbox to open the data and download the data and do some pre-processing. But I would say, yes, the toolbox is not related to the accuracy of the results that you obtain. The toolbox allows you to get and retrieve the data, and what you do after the pre-processing and the interpretation, your interpretation of the data is itself the one that defines the results. So the toolbox is working really fine. The results that we obtain when downloading the data are as accurate as they are, and what you do after is the one that defines, I would say, the final accuracy of the data.
Okay, thanks a lot, Gaza, for the explanation. So we will have to stop there for the question to go to the next presentation, but thanks again for joining.
Thank you.
Yeah, so now we will go to the Jupyter tutorial, sorry. So yeah, Alexandre, whenever you want, you can join us and start the presentation.
Yes, thank you, Gaël. Hello, everyone. So I'm Alexandre Morin from Noveltis. I'm going to share my screen to present to you the Jupyter tutorial. So I think you should be able to see it now.
Yeah.
Is it fine? Okay, perfect. Okay, so in this notebook, so I've decided to as a topic to choose marine heat waves in the East China Sea. So marine heat waves, so you would define them as a period of anomalously warm sea surface temperature during several consecutive days. And of course, this is an event that raises increasing awareness because, well, such events can have very strong impacts on ecosystems, biodiversity, and after that, local economies, fisheries, and so on. And this is why understanding and monitoring those phenomena is absolutely crucial, especially in our current context where such events are expected to increase in frequency or intensity due to global warming. And so in this notebook, we are focused on the East China Sea, so which is located at the center of several influences here. It's at the end of the Sea of Japan, of the Yellow Sea. There's the Kushio Current that passes in this area also, which is why it has a very changing thermal environment. And also this is why it is particularly sensitive to marine heat waves. So let's get going. So in this notebook, we'll be working with Python. So if you already worked with Python, you should be already familiar with several libraries that we're going to use. NumPy, for example, is very commonly used for computing scientific arrays. Xarray is the mostly used package to deal with netcdf data, which is the file format in which most of the Copernicus Marine Service products come with. Well, SciPy is a very wide library which provides many scientific and mathematical tools for statistics, optimization, signal processing. So which is, well, often essential for scientific computing. And then Matplotlib and Cartopy are used to draw the different maps and plots during in the notebook. So if you are using the Copernicus Marine Service Jupyter Hub, when opening a notebook, you should have access to the Copernicus Marine Jupyter kernel. So make sure you select it because then you will have all the different libraries already installed, and you will have and the notebook will be already ready to be executed. Now, next section, let's take a look at the data that we're going to use. So as I said, we're going to study and analyze marine heat waves. So the dataset that we're going to use is a dataset of sea surface temperature. In our case, it will be an observation dataset from well, the combination of several satellite observations. So here is the Copernicus Marine Service dedicated page to the product. So basically, the temperature, as I said, are derived from several satellite observation made in the frame of the European Space Agency Sea Surface Temperature Climate Change Initiative. So what's interesting in this dataset is that it covers a very wide period. So it's from 1982 to 2023. And because having several decades of data is very helpful when we want to study long-term trends and the evolution of certain phenomena, especially in climate science. So it has a resolution of 10 kilometers approximately. And yes, this is most of the important information that you have to take away from this page. And also we're working with daily data. You will see why in a few sections, but it's to be able to compute marine heatwave events. And one other thing that I can also mention is that on this page, you also have access to the user manual and quality information document if you want to go even deeper in your exploration of the product. So feel free to read them if you need to. So you've already had a presentation on how to retrieve data using the Copernicus Toolbox. So here you can see a simple example of how I used it to retrieve the data I've mentioned before. So all I'm doing is importing the Copernicus Marine library, which is already installed in the Copernicus Marine kernel of the notebook, logging in and entering my credentials. And then defining the area of interest around the East China Sea, so defining a latitude and longitude box, and then entering the data filters in order to use a subset function and retrieve the product. So you've already been shown this, but here you just have to click on data access to retrieve the ID of the dataset and copy paste it here. Here is the variable that we are retrieving, so sea surface temperature, SST. Here is our area of interest, and here are the bounding dates that we want to retrieve. So we want our 42 years of data. So I've already pre-downloaded in order to save time. And well, you can see I've done it twice already, but our dataset is downloaded. So we are ready to take a look at our temperature data. So when you use X-ray and you open a dataset in the Jupyter notebook, here is what your dataset it looks like when you open it simply in a cell like this. So we can first see that we have indeed 3 dimensions in our dataset, so latitude, longitude, and time. You can check that the time values are consistent with your request. Here you can see it indeed goes from the 1st of January 1982 to the 31st of December 2023. So we have the full dataset. This is consistent with what we asked. You can also check that the latitude and longitude are consistent with the area of interest that you have defined. And here we have a variable, analyzed SST. And if you want to read more details on the variable, you can click on this icon here, which displays the metadata of the variable. And it gives you here, for instance, well, the full name of the variable, the unit. This is pretty important. Here it's in Kelvin, so we may have to do some conversions in order to work with Celsius degrees. And yes, in this dataset, we also have some general metadata, contact information on the authors, references, and so on. Okay, so now that we've just opened the dataset simply in a Jupyter notebook cell, we can probably go further and visualize on a map what the sea surface temperature heat map looks like. So first, let's just plot a random date. So here I've arbitrarily chosen the 25th of September 2021. And then those lines here are only meant to draw the map. So we can go quickly over this, but here we just add the coastlines. Here we set the extent around our area of interest. So we just zoom in on the map, basically. We add the green lines. We just sort of clean the dataset to avoid some labels that we don't really want there in order for that to be aesthetically more pleasing. Here we select in our dataset using the cell method the random date, the arbitrary date that we have chosen. And then using p-color, we color the map according to the temperature here, converted to Celsius. And this is just to add the color bar in the legend. And we look at this random dates. Well, what we can see is that even in a rather small area, we could say, we already have a strong spatial variability of the temperature. So here from like 24 degrees to almost 30 degrees on this day, which is quite consistent with what we said in introduction that, East China Sea had quite a changing thermal environment. What we could do more would be to plot consecutive dates and animate them in order to see the changes and how it varies with time. But yeah, this is something you can do if you do the notebook at home. Okay, so this is just a random date, and as we said, marine heat waves are quite important to look at, especially in the context of global warming. So let's try to highlight that and compute the long-term trends of temperature. And in order to do that, we just have to perform a few steps. First, we need to calculate the spatial average of the dataset in order to transform here this three-dimensional dataset in a single-dimension dataset over the time dimension. So transform this into a time series. So we have to do the average over the two spatial dimensions. So this is what is done here using the mean function of the X array. Then we have daily data, if you remember, which of course, if you plot 40 years of data, will show a strong, seasonal variability. And in order to erase that, we can just resample the data and compute yearly means. So this is what is done here. For example, to have yearly data and compute the yearly mean. And finally, to derive the trend, we'll just have to do a linear regression, which we'll do here with NumPy using the polyfit function. And if we plot all this, this is the evolution of the average temperature in the area over the last 42 years. And you can see that there is a very strong here increasing trend of about 0.2 degrees Celsius more every 10 years. Of course, we could do some deeper analysis and try also to compute the correlation of the trend with the actual data. We haven't done that here, but it's something we can do. And we also see that there is a strong interannual variability here, with some very strong years here in the early 2000s, and here in the early 2010s, we have some of the lowest temperature over the 4 decades. So this shows us even though the global trend is increasing, there might be other factors that also drive the temperature, the sea surface temperatures in the area, which would have a variability that is perhaps decadal and not I don't know, yearly or seasonal, just like the winter summer cycles we usually have when working with temperatures. So this was an analysis of the average temperature of the entire area. So now let's refine this and try to compute actual marine heat wave events. So a standard definition that can be used is that a marine heat wave occurs when the sea surface temperature exceeds the local 90th percentile of reference period for at least 5 days. So in this notebook, we try to take inspiration from that. So first, we need a long-term reference period. So in climate science, such periods usually cover 30 years of data. So we will take the 1982-2011 period of our dataset. And using this, we'll compute the 90th percentile and the average sea surface temperature for each day of the year regarding this reference period. So this is what we do here, computing the 90th percentile climatologies and also average. You will see why, because we're going to need them for visualization. And if you try to, now we are going to try to look at the marine heatwave events on a single year. Now that we have computed our reference baseline. So in this example, we'll look at 2023 and do visualization of the actual temperatures of 2003, which is here the red line, and the average and 19th percentile, which are respectively the black and orange lines. And we can see here that over the year 2023, we have a very long period here going from the, middle of August to, we can't really see if it's interrupted here or not, but at least to, let's say the beginning of November. We have a very long period of anomalously high sea surface temperature in the area. So this is definitely a marine heatwave event. We also have a small one here in the from March to I would say beginning of April. And you can reproduce this on any year that you want in the data. This is quite arbitrary, but if we look at 2005, we have one small marine event here. And here on the contrary, anomalously low temperature. So feel free to explore if you do the notebook by yourselves. But we can even refine this a little more by trying to classify marine heatwave events depending on their intensity. So this is just a small figure to explain to you the principle of the classification. So as you can see here, we have the average and 19th percentile of the baseline, and the goal is to know if the actual temperature go just above the 90th percentile, or go above 90th percentile plus the delta here between average and 19th percentile, or if it goes above twice this delta or 3 times this delta. So this is what we'll do here with our 2023 marine heatwave events. So basically, all we have to do here is to compute on ourselves the delta and accumulated it several times. And for example, here we can see that during the marine heatwave events of end of summer and fall 2023, it did goes above the next threshold here that we have defined. So in our case, this would make it category 2 marine heatwave. But so this is quite a fine visualization, but this is only a visualization. And now let's try to do some more quantitative analysis by computing marine heatwave indicators. And so we're going to just compute several simple indicators. So basically indicators of frequency and intensity of the marine heatwave events. So here we compute the actual, here in those cells, what we do is that, we compute the days where we are above the 90th percentile of the reference period. And then we'll filter out the periods that are less than 5 days, because we count marine heatwave events only when there are more than 5 consecutive very warm days. So this is what this function does to filter out the short runs of warm days. And so we are still using the year 2023. And if we look at the indicators that we have computed by counting the marine heatwave events, we can see that we've detected 5 marine heatwave events, one with a maximum duration of 89 days. So this is quite consistent with this that we had found here. And some other maybe not very visible. For example, here, for instance, we could go a little bit above the threshold, which should count in the 5 heatwave events that we maybe had not detected visually. So we have median duration of 9 days, and compared to the average baseline, the mean intensity is of 1 degree above the baseline, and the max intensity is almost 2 degrees above the baseline. And now we have studied 1 year. I can see that I'm running quite a bit of time, so I will try to wrap this up quickly. So here is the computation on all the 40 years of data here, as you can see. So this is the frequency, so by number of events per year. Here is the duration, maximum and median per year. And here is intensity, average and maximum, also every year. And we can see that contrary to the temperature values, we don't have a clear increasing trend when looking at marine heatwave events. We can see that we alternate period with few and low intensity events with periods of very strong and very frequent marine heatwave events. So first, in order to have a more precise idea of a potential trend followed by the data, we should probably compute more years of data if those were available. But like having old observations, especially with here we had the satellite observation of sea surface temperature, it's quite difficult to find such data. And also we also try to correlate these results with other phenomenon, like for example, one that is very influential in this area is the El Nino Southern Oscillation. So we could try to correlate those results with the oscillation to see if there is an influence. So yes, we are reaching the end of the tutorial. So there are a few exercises that you can do if you do the notebook by yourself. I mentioned some of them already during my presentation, but it is a global dataset covering all the world, so you can reproduce this analysis anywhere you like. And yeah, feel free to do exercises, and I hope that you enjoy this presentation. If you have any questions, don't hesitate. Thank you for your attention.
Thanks a lot, Alexandre, for the nice tutorial. It was really interesting and quite on time with June months. So and yeah, we have a few questions for So we have a few questions for you. The first one about the dataset. So the temporal extent of ODC is January 1982 to December 2023. If we want to analyze current marine heat waves event, do we need to combine datasets?
Well, you probably need to find a dataset that covers a very recent period. In order to combine, for example, this new dataset to the one that I've shown, well, you would probably have to analyze a little bit if the two datasets are consistent or not. I think, for instance, you would have to analyze what are the sources of the temperature data. Here it's satellite observations, but for example, you probably wouldn't want to combine them with a model output or a reanalysis, for instance. So if you want to combine them, make sure that the two datasets are consistent. But if you only want to study recent data, maybe you can just use the dataset that you've found to have data on 2024 or 2025, for instance.
Okay, thanks. Yeah, and there is also real-time data on the catalog available, so you can almost see in real time the heat waves. So Okay. So this one, I think it was around part 5 of your presentation. The random date in T-plot, is it actually random or do you have things to consider, such as news, usually this month, marine heat wave occur more frequently, etc.?
No, as I've mentioned, I've chosen this date totally arbitrarily. This was only meant for data visualization without really seeking a particular event. So yes, this was actually it was just for the sake of drawing a map and visualizing the data.
Okay, thanks a lot. I think the next question, maybe the person didn't see well. How is the data from 1982 to 2011, and we are choosing 2023. So I think the data set was going up till 2025, if I'm not mistaken.
Well, this one was going to 2023. Well, I've noticed some changes during the course of developing this tutorial, so maybe the datasets on the satellite version are still being, I don't know, maintained or developed probably. Well, I don't really know where the user has seen that it was from 1982 to 2011. I'm not exactly sure where this information comes from.
Yeah, I'm not sure that maybe it's another data set or something like that, but it was just to be sure. Okay. Oh, thanks. Sorry. So this one has several questions in it. Which part of your graph is telling me that there is an heat wave, and how much do the ocean should have a normal SST? Should it differ between locations?
Well, I think you're referring to the graph where I'm showing the baseline 90th percentile and the actual temperatures that may go above. So, well, marine heat waves are defined by well, period of at least 5 days where well the actual temperatures go above the 90th percentile of the reference period. So on the graph, we could clearly see at several locations that well here in our example, the 2023 SC surface temperature were above the 90th percentile threshold. So once you are above that threshold, then well, visually we could see that it was for more than 5 days. You could deem this anomaly as a marine heat wave event.
Okay, thanks for the explanation. I think we have time for one more question about your presentation and marine heat waves in general. What can be the impacts of marine heat wave on phenomena like precipitations?
Oh, this is a strong question. Well, I guess the it would probably I don't know maybe probably trigger more evapotranspiration and trigger precipitation elsewhere of the region, but here from the back of my mind, like it's difficult to answer. Sorry.
Yeah, it's a whole subject, so yeah. Okay, so I think this one will be the last one. Is it possible to use Odyssey L4 as a baseline and use NRT data for the analysis?
Well, I think that as long as you make sure that there are not systematic biases between the two datasets that you're using, so as long as you make sure the two datasets are consistent, I don't think there is a problem doing this.
Okay, thanks. So we will have to stop there for the question. I think that was the last one directly concerning the presentation. Yeah, thanks again, Alexandre, for the tutorial and the presentation. Okay, so now we will do a small break, sorry. So feel free to take a look at the polls. We prepared a fun work cloud to get to know you better. So if you want, you can share what you work on inside. And yeah, if you want, also grab a coffee or discuss with each other, and we will see you in 10 minutes. Welcome back, everyone. So we will go to the next presentation, which is the QGIS tutorial by Daria from Novelty's team. So welcome, Daria, and you can start the
Hello.
tutorial whenever you're ready.
Thank you. Great. I will start sharing my screen. You see my screen now?
Yeah.
Yeah.
Yes.
Okay. Great. Well, hello everyone. My name is Daria. I'm from Novelties, and well, today I'm here to present you this exercise in QGIS, which is dedicated to study of salinity variability during the 2022 monsoon transition in the Bay of Bengal. And this is going to be more like overview of a tutorial, which the full version of which you can find on a video, like in format of a video, on the website, and also the PDF format if you want literally like step-by-step procedure, because here I'm not gonna show every detail because I don't have much time. And well, first I will tell you a bit of context of this topic that we're gonna look into. Then I'll show you what product I used from Copernicus Marine Service platform, and then of course the tutorial in QGIS itself. So first of all, as I said, we're gonna look at the Bay of Bengal, and well, as you can see here on the slide, the Bay of Bengal is, well, I think everyone knows, but still it's a northern extension of Indian Ocean, and this is one of the most dynamic regions in Asia, and each year it undergoes dramatic changes in its climate, let's say, due to the South Asian monsoon. And the monsoon season actually starts usually from June, and it lasts till September approximately. And well, monsoon, it's a large-scale seasonal wind and precipitation system, and it drastically influences the atmosphere and the ocean as well. And today we exactly going to look how it influences the ocean. And well, the main influence on the ocean from the monsoon is of course the heavy rainfall and the extensive river runoff, because also in this region we have many rivers that well end up in the ocean. And salinity, but seawater salinity, what we're gonna study today, is one of the main ocean parameters, and it is influenced by the monsoon, because, well, of course, as I said, of rainfall and of river runoff. So, well, and yeah, seawater salinity is it's a concentration of salt dissolved in water. So of course, if we have a freshwater input from rain and rivers, we will have an impact on the salinity itself. So that's what we're going to look at. Very quickly, I'm going to show you which product I've used, and that's a global ocean physics reanalysis product from Copernicus Marine Service. And we focused only on salinity, seawater salinity, monthly mean variable. So let's go to QGIS, and here we are. I will just adjust a bit. So as I said, the project that I created is already fully ready. I have all the data already uploaded, so I'm going to just show you mainly like the results and some intermediate steps, but not in details. So first of all, what we want to say, we wanted to see, well, the change of seawater salinity on a surface level, on a deep level, we will call it deep, for the area for the pre-monsoon and monsoon season. So pre-monsoon season is usually from March to May, and the monsoon season, as I said, is from June to September. So here you can see that we will look at these seven time frames, and we will add them via this plugin, which is called NetCDF2 GIS plugin, which was developed here at Novelties, which basically allows to import the different NetCDF files in a QGIS a bit more neatly and a bit easier than the default option of QGIS. So in this plugin, you just basically can click on plus and go to your data, or you can For example, like what I usually do, you can just drag and drop the files you need. Here I have two files. So one is for a level of 0.49 meters, which is called surface level. And another one is 55 meters, almost 56 meters below the sea surface, which we will call a deep level. And you just right click, you go to add layers, you choose the timeframes you want, and you add, and they will appear in your project. So I already have them added. I will just activate it, and we will see already how it looks like. So that's the salinity for surface level. And here you can see that's for March. I will zoom a bit. And then if we untick boxes, we will see how it changes throughout pre-monsoon season. And this is still the pre-monsoon, that's for May. And then how it changes for monsoon season from June to September. And you can clearly see that more we go into the season, into this period, the more we see this dark purple plume here on the coast. And that's exactly like if you look at the scale, you can see that, yeah, the darkest darkest color corresponds to lower values of salinity. So it means that the water there is less salty. So you can see that literally on the coast, we have more and more impact. For example, from June, and starting from June, you can see yeah, impact of river runoff. And this is for the surface level. And we will also look at the deep level, well, which is only 56 meters, but already enough to have some conclusions. So here you can see this layer, and you see that it's not actually touching the coast, right? You can see that here the pixels, the data is not reaching further, because, well, it just means that it's not available there, just because, well, it means that it's not that deep. The depth is not reaching the same value. And here, that's for the March, what we see now. And if we just untick the boxes, you can see that, yes, we do see some fluctuation. We see some turbidity here. You can see that it changes, but still the scale is the same for your information. And you can see that it does change, but it doesn't change drastically. So basically, that with this little comparison, what we want to see is that at that level, we see that river runoff and rainfall as well, it does not impact at this level, at the depth. And it is true that mostly surface levels are influenced by such phenomena. And so yeah, the less salty water is also less heavy. Yeah, that's why it stays on the top. So that's it for this little comparison, and we're not gonna focus on deep levels anymore. I mean, we're more interested in surface level, because we can really see the difference here. And what we wanted to see is the well, we actually want to have more representative, better representation per season, so pre-monsoon and monsoon season. And for that, we need the average. So average, basically, well, everyone knows what's average, right? We just take the sum of 3 months for pre-monsoon and 4 months for monsoon period, and then we divide by 3 and 4, well, depending on the season. And for that, we use a raster calculator function here. And basically, the expression would be, for example, would be March plus April plus May, and all divided by 3. And I will also add like that. So yeah, and in this raster calculator, you also can set the output coordinate reference system. But what is important to note is the reference layer. One of these layers should be noted as reference layer for all the for extent and so on. And then you run it, you will have something like this. So this is seasonal average for pre-monsoon period. So we can see that, yeah, mostly, of course, here salinity is going to be lower next to the coast, because we always have some river runoff, and impact from inland water. And we did the same calculations to have a monsoon seasonal average, and you can see that it is now much more different. You can see much more areas that are affected by lower salinity. If we just do that, just to see again, you see. And what we wanted to see next is the difference between them two. So to see the difference map is very useful when, well, we have two maps, right? We have a pre-monsoon and monsoon average, and it's nice to see them like one next to each other, but it is more representative if we have a difference between them. So to see where the change exactly is, so where it was a positive or negative change, or where there was no change at all. And for the difference, we use exactly the same function. It's a raster calculator, for which we basically choose, for example, pre-monsoon minus monsoon, or the opposite, just depends on color. The color is going to be inversed. And the result is this. We also can adjust actually representation style of a layer. Like, for example, if you double click here and you go to symbology, sorry, it's here. You can here you can adjust many things, many parameters, just to make your layers more representative for your needs. For example, here we use another scale, which is from -3 to 3. You see the negative values are in blue, the positive are in red, and white is all neutral, we can say. And well, red means that salinity increased between pre-monsoon and monsoon, and the blue means that it decreased. So yeah, here we clearly see that which areas were impacted by the decrease of seawater salinity. So as we already witnessed it was mainly here in the coastal region. Also, we can see an interesting impact here. We can see a little patch of lower, of a patch of water which had less, like, the salinity, seawater salinity decreased also here, which we cannot say why, because we would need more analysis, more more in-depth analysis. Here we can see that in some zones it increased slightly. Here next to Sri Lanka it kind of increased a lot, we can say, like it's quite a bright spot of red, and there are many places in which it's kind of neutral, close to white shades, meaning that there were not much change present here. And for the next tool we wanted to show in QGIS, which you can use for the data related to ocean as well, is contours. So basically, we don't need this one now. We would need this layer, for example. So next one is to do a contour lines, which you can also find here in the raster extraction tab in the processing toolbox. It's called contour, and here you basically put the layer which you want to use as a reference, and then you will put interval between contour lines, which basically tells you how dispersed lines will be, so how populated with lines your resulted layer will be. And when I'm saying lines, it's basically with isolines which delineating the areas of the same salinity. So usually it's actually used for elevation. For example, on many maps, you can see the elevation like in the mountains, right? You see the lines, and by these lines, you can see when it's going up and going down. So it's basically the same here, but use it for salinity to see the zones that are sharing, let's say, the same salinity level. And for example, now we see our monsoon seasonal average. And if we show our lines, you can see that. And with the labels, you can see the values of salinity. So we can see, for example, here, more like closer in like outside of a bay, closer to the outside of a bay, we see the salinity is high, say, and then it's slowly kind of dilute, slowly going down towards the coast. And in the coast, you see it goes Like for example, if we zoom in here, you can see it's literally 5, and there's 35, right? And yeah, you see that the lines here are more present, more dense. And we did the same to see for the pre-monsoon. Sorry, up. And you can see exactly the lines delineating. You see that they are less lines here. I mean, they're still dense, but they're less going out of the coast. And what we also can do, we can also right-click on our layer and go to filter and filter it by some specific value. We just decided to use some arbitrary threshold. We called it. We decided it's going to be 30, for example. We can click on it, and we can basically only highlight the zones with lower than specific threshold salinity level. So for example here, and if we do the same for the second one, and we compare them, you can see that, yeah, we already saw it, but it's just another tool to see that indeed during the monsoon season, the area of lower salinity water did extend further into the bay. And the last but not least is a quick presentation of a small tool, which is actually not a tool of QGIS, it's a plugin. And you go here into the tab of plugins, and you go to manage and install plugins. So usually this plugin is installed by default. It's called a profile tool. Yes, here. Usually it is installed by default, but it depends on your version of QGIS. Maybe you don't have it and you just install it, but it's quite quick. You just have a small install button here. You click on it and it's basically done. So you need to tick the box so it will appear in your among your tools here. So I already have it. It's this one. I click on it, and then there's this window appearing. And I will just untick something. Okay, thank you. Some error. Well, here what we want, profile tool basically allows us to draw a line along a line on top of a layer we have, and basically have a variation of specific variables along this line. So it's like a transect. And that's a quite nice tool to see also more in details, more like a plot, right, with all the values. So for that, you would first need to add to this table the layers you're interested in, and we're going to look at pre-monsoon average. We need to highlight it and then click add layer, and then monsoon, add layer. And by right-clicking, just clicking on the color, you can change the color. I'll change it really quickly. So we have 2 different lines on a plot, so we can really see what's which one is which. And now you can see that our cursor changed to this little cross. So we will draw a line from the coast, and let's like kind of diagonal outside in the bay. And you see I drew the line, and you actually can continue the line. The line can be whatever you want. You can see it's what it adds. To finish it, you just double click and it's done. And if you don't like it, well, it's a strange thing, right? So you just right click wherever and it will disappear. So I just had I'll have another line up like this. And here you can see a plot. With green is a pre-monsoon salinity, and blue is monsoon salinity. And you can see that along the transect, so starting from 0, which is at coast, and going like 20 points, right, outside, we can see that at mostly around like this part, right, it kind of gets on the same level. The 2 lines, they approaching each other and stay at the same level, same value, meaning that outside of a bay, they are close values of salinity. But in coastal region, you can see a big difference, especially here in the beginning. For example, here for the pre-monsoon, it starts at the point that you chose, starts like at 19, right? And for monsoon, it's at 6. So it's a big difference. You can see how it goes. And then, yeah, it kind of goes to the same plateau. And you can save this plot as PNG or SVG, whatever you want. You click on Save As, you choose where to save it, and it will be then saved exactly like this. I will show you real quickly because I already have it saved. The only thing is, well, you can use you can use this plot for something, right? The only thing is that it doesn't have options to add, I don't know, like titles or axes, names, and so on. But this you would need to do yourself in some other external application. But it's a nice tool to know to use in QGIS. So that is it for this tutorial. It was a bit quick, but as I said, yeah, you have a step-by-step procedure also available in a PDF file and in the video. So yeah, if you have any questions, I am here to answer them.
Thanks a lot, Daria, for the tutorial. So yeah, we will go to the questions. For now, we only have one, which which we'll go over too. So can these datasets be useful in observing seasonal changes in coastal areas as well? Anything we should keep in mind before using them in smaller or coastal areas?
Mm-hmm. So, well, first of all, yes, the more like general answer, but basically all data sets can be used in any other region as well. For example, the tutorial I showed, you can repeat it in the same area with different variables. You can add some seawater temperature, for example, as well. And you also can use this data in our different data in different zones for different studies. So it's very like interchangeable. And regarding these data sets, can they be in visual observational changes in coastal areas? Well, yes, because the data is quite precise on the coast as well. But of course, this data has a resolution. I cannot exactly tell what is the resolution, but of course we should keep in mind that for some, as I said, in the smaller coastal areas, it might not be the resolution might not be enough. So we see pixels, and if you really zoom in, and we see that they actually do not cover some specific zones next to the coast. And then, yeah, so this we should keep in mind. And I think that there might be, well, it depends on your application and on your zone. There might be specific data sets which are really for specific sea or specific zone, including like some coastal areas. So yeah, you would need to look at that for sure. So it's really like you need to pay attention to resolution. And also, yeah, I mean, in very small base, for example, little, like, I don't know, little coast, yeah, sometimes you just don't have that good, like data is not that available for small places.
Okay, thanks a lot for the detail. We'll go to another question, being where do we get our raster datasets?
Well, we download them from Copernicus Marine Service platform. Yeah, I didn't show you how to do that because, well, I don't have time, but I think you already seen it in previous webinar, for example. And also, yeah, you can always check. There are many resources, many articles available on the website, which basically give you a step-by-step procedure.
Yeah, exactly. And the replay will be available also if you want to have a look, so no worries. Okay, have you studied the impact of this in increased cyclone formation in the Bay of Bengal?
No, I just looked at the salinity, as I said, pre-monsoon and monsoon seasons, during these two seasons. And of course, yes, cyclone will change, will bring its impact to the sea surface, and well, with at least waves and with probably currents also. So yeah, the salinity will also be impacted. We can see some patterns, but yeah, I did not focus on that.
Okay, thanks a lot. Okay, so I think you said it during the presentation, but what were the data sources for salinity?
Well, I would say again, Copernicus Marine Service.
Yeah,
website.
but I think
If
maybe
I,
like model data, satellite.
No, I'm not sure. I'm not sure. I talked about, I mean, because, well, the data depends on the provider. So
Yeah.
I don't know. You think you see some other meaning to that question?
No, I will put the question on the side if we didn't answer understand the question correctly.
Okay,
I think the
yeah, we
people
can look at it.
can rewrite it. Okay. Another question. Can other datasets such as chlorophyll be visualized like salinity? I guess with QGIS.
Yeah, of course. Any variable. Well, most of the data of Copernicus Marine Service is presented in the same format. It's a NetCDF format, so it's a big raster layers, and you can download it for specific regions and stuff. You don't need to download everything, and yeah, all of them. QGIS is very good with raster data, and as I told you already, you can apply different styles and visualize it, make it more I don't know, easy to look at, more comprehensible, more popping. Yeah. So yeah, salinity works very well. We already had some we had some tutorials already about salinity previously. So yes.
Okay, thanks a lot. So we have a few more questions. This one, I think, what are the impacts of the salinity variation? I guess maybe on marine ecosystem instead of just the monsoon system.
Well, yeah, the salinity is important to the ocean ecosystem in many ways. First, of course, yeah, about marine habitat, of course, because when it's well, too salty water is not good, and not salty water enough is also not good for some species. So it impacts also the food availability for marine animals. And for that, well, we need to expand the analysis by including some more data, external data as well about animals, for example. But it's also important to the ocean itself about I think it's called density stratification, mixing of water levels, because well, so salty water and salty water is not really how it mixing one with another. So yeah, the impacts are, well, these impacts are not that drastic because they are, but at the same time, it happens seasonally, like each year we have the same picture. So it's kind of, that's kind of it. So yeah, but of course, to have more impacts, you need to have a bigger analysis.
Okay, thanks a lot. So I think that was a clear explanation. We will do one last question about the presentation. So this one is a more general question, not really about the presentation. But do we only have salinity to work on in the Bay of Bengal? So you choose to use salinity, but you could have chosen other parameters.
Yeah. Yeah, of course, you can choose whatever you want. And for example, as I already also, I think, mentioned it in a video, that for you, what you can do if you want to explore this data set or just explore QGIS, you can repeat this tutorial for yourself and add some little exercise by, for example, mapping seawater temperature and comparing how seawater temperature changed during the monsoon season and pre-monsoon season. And also if you can see if there is any correlation between seawater temperature and salinity. And well, after you can even look at the atmosphere data as well, because well, it's a rainfall, right? It comes, so we can also see the precipitation, temperature, so in the over air. So there are many things you can actually study there and just expand this tutorial to, I don't know.
Okay, well, thanks a lot. I think that was the last question about the presentation. So thanks again for the tutorials, and you have plenty of kudos on the chat of the event.
Thank you.
See you. And yes, so we will go to the last tutorial of today, which is the Air Studio tutorial by Simon. So welcome, Simon, and yeah, you can start whenever you're ready.
Yes. We'll share my screen. Do you see my screen?
Yeah, we see it.
Yes. So hello everyone. My name is Simon Millet. I'm a scientific engineer at Noveltis. and I will be your trainer during this session in R about the Kuroshio current. So after exploring the NetCD file, we will make a basic plot of sea surface temperature, then basic plot of sea surface current. Then we will see the seasonal variation of the current, and finally we will see the evolution of the current during El Nino and La Nina period. So this training focus on the Kuroshio current, often referred to the Gulf Stream of the Pacific. It is the powerful warm western boundary current that flow northward along the eastern coast of the Philippines and Japan. He has an important role on redistribution of heat, salinity, and energy across the Pacific Ocean, and therefore has an important impact on fisheries, weather pattern, and marine biodiversity. So in this training, we will begin by visualizing maps of sea surface temperature and sea surface current using vector arrows. Next, we will create an animation over the course of 1 year to observe the temporal evolution of the Kuroshio current, so the intensity and the position. And finally, we will compare 2 specific months, so January 2011 during La Nina event and January 2016 during El Nino event. So in this training, we will allow to see the evolution of different parameters, sea surface temperature and current over time. So in this training, we use a Jupyter notebook, but it must be set up with all necessary libraries. So in this training, we need 9 libraries. So there is ggplot2, it is for creating graphic. Dplar, it is for manipulating data. RColorBrowers, it is for color palette in plot. Therefore, it is an interface for NetCD file format. GridExtra, it is a library to arranging multiplot on a page. Lubridate, it is for date time data. ggquiver, it is for creating a quiver plot in ggplot2. Skulls, it is a library for Skulls map data to aesthetics. Magic, it is a package for image processing, especially for create animation. So first we run all the libraries, but if you are using another support, you can use this command line to download all the necessary libraries. So the data are available in the Copernicus Marine Data Store. You have the link here. You can explore all the products available with many filters and to select the region you are interested in. In this training, the data are already downloading in the folder data here. But here you have the characteristic. If you want to try to download, it is possible. You will need you to have your own Copernicus Marine credential, username and password. So in this training, we will use the global ocean physics and area analysis in the Pacific Seas. We only use the surface and the variable. It is the current, the temperature, but in the dataset there is two the salinity and the sea level. And the time period is monthly means from January 2010 to June 2018. So first we set the path of a NetCD file. We load the NetCD file with NC open. And you can see here the information about the NetCD file. So there is a file variable there is the current here. Here the sea surface height. Here the temperature, and here the salinity. Here it is the dimension of the dataset. So there is time, depth, latitude, and longitude. The size of depth is 1 because we only download the surface. And here it is the global attribute to have more information about the dataset. So we load here all the variable. And it is possible to visualize some information, for example, the dimension of variable temperature, that is longitude, latitude, and time. And you can see equally the value of 1 longitude, 1 latitude, and 1 time. That is here 23 degrees. We can do the same for the time, but you can see here it is a number, not a date. So to convert in the date, we use the function as POSIX here, and we put the variable here and the origin. Here it is January 1970. It is noted in the characteristic of the dataset. It is noted here. And so we run the cells, and you can see now it is a date, not a number. Here. Now we make a basic plot of sea surface temperature. So first we determine the figure size, and then we create a data frame of temperature that depend only of longitude and latitude, because we select the index of time that is 8 ici. So we can visualize the data frame but of temperature that depend only of longitude and latitude. Then we can plot the data frame. So we use ggplot function. Then we use geomtile to add the sea surface temperature data. So with the data frame we have created with longitude, latitude, and temperature. Here it is the function to the color scale. So we put blue for low value, red for high value, white for the middle of value. It is 28. Here it is for title and subtitle, and here aesthetic option. And then we save the figure in the folder figure here. You can save here. So we run the saves, and we can see the temperature in August 2010. So we can see the variation of temperature along the Kuroshio current with there is a marked thermal variability, especially here. So now we will see the surface current. So first we create a data frame. So it is the same method that we have seen before. We create a data frame dependent of longitude and latitude because we select the time. So there is a free variable of current, that is the eastward, the northward, and the norm of the current. And we create here the second data frame specifically for plotting the arrow on the map, because there is many points, and this data frame the new data frame is based on the original data frame, so this one, but we reduce the number of points to make the arrow visualization clearer and more readable. So we create a new data frame here, and we plot. It is the same code that you have seen before, but we add the geom quiver here with the new dataset df space, and we can plot the map. So we can see it is the same date in August 2010, and you can see the sea surface current, and you clearly see the Kuroshio current. You see the direction, the meander, and the weight of the current. So we have seen how to map, for example, the current for one date, but it is interesting to examine the evolution of the current over a year. So to do this, we will compute the monthly mean current field from 2010 to 2018, and then plot the corresponding map for each month and visualize in an animation. So first we will create a data frame, then we compute the monthly means current, then we plot all the current map, and finally we generate animation. This is the step of the steps. So first we create the data frame. It is the same method we have seen before, but we add the corresponding month. So if it is January, it is 1. It is in February, it is 2, etc. So you can see the data frame, longitude, latitude, time, current, and the months, corresponding months. Here it is the cells to do the monthly means. So we do the average of current here for one longitude, one latitude, and 1 month. So for each longitude and latitude, and each month you have a value of the current, and then we convert the result in data frame. And then we create a plot function. So it is the same code we have seen before, but we put here in a function to avoid to do 12 times to run 12 times the same code. So, and here we create each figure. So for each month, for January, February, etc., we plot the figure, and the figure are saved in the figure here, figure for GIF. You can see the creation of the figure. And then we select the directory of all the figure, and then we load the GIF animation. So we can see here the evolution of the current, sea surface current, from January to December. The current not sorry, the current change with the season, but not ugly. There is a minor variation. The current seems slightly stronger in winter than in summer, suggesting a seasonal intensification during this time. Now we will see the evolution of current during El Niño and La Niña period. So for this, we first identify the index of corresponding date, so January 2011 and January 2016. And then we extract the current feed for these two periods, and finally we will compare the result. So first we select the index. Then we create a data frame for here for La Niña period in January 2011. Then we create a data frame with less data for Beaver, and then we plot the data. So you can see here the sea surface current during La Niña period. We do the same for El Nino period. So you can see here, there is some difference of meander between El Nino and El Niña, especially here. But we can plot the same figure, but with the difference, the difference of the norm of current between El Nino and El Niña. So here you can see the difference. So when it is in red, it is the current during El Nino is more important, and if it is blue, it is during El Niña, but the current is more important. So during El Nino period, the cursor current become narrower and weaker than during El Niña. During El Niña, the current is move in the north than in La Niña period. So you can see here the difference between El Nino and between the two events. So now the training is now finished. So if you have a question, do not hesitate.
I forgot to open my mic. Thanks a lot, Simon, for the tutorial. For now, we have one question about your presentation. We will see if more come later. So the question being, could this type of study be applied to other currents, like other Western boundary currents, for example?
Yes, it is possible to visualize, for example, the Gulf Stream current. There is a current move over seasonal variation with a seasonal variation. And it is important to see to know the current because there is many biological phenomena because there are some fish that follow the current. So it is important to know the current.
Okay, thanks a lot for the explanation. So the second question, I still have an issue with my computer.
Right.
Okay, now it's working. So what are the other factors except El Nino and La Niña that you measure, and except the two parameters you showed during the...
So during this training, we see an example of the factor of El Nino and La Niña, but it is possible to see other factors like motion. Maybe it is change the current direction or the intensity. But in this training, we focus only on El Nino and La Niña period.
Okay, thanks. So yeah, another study to be done now.
Yes.
Yeah. Okay, thanks a lot. I think that's the last question about the tutorial, so not a lot of question today. Well, I guess we will stop there then. Thanks again for the presentation and the tutorial. Okay, well, so thanks again to everyone for their presentations and to you participants for your participation. So we are reaching the end of today's session, and yeah, we hope you found the session useful and that you could learn a bit more about what is the Copernicus Marine Service. Also, so before you leave, in case you haven't noticed, the full tutorials are available on the website along the scripts, the data, the documentation, and the full video tutorial. So if you want to look deeper into the tutorials, you can have a look on the webpage. And then finally, before you leave, I just want to remind you that there is a section on the website next to the Q&A reserved to the polls. So we would really appreciate to have your feedback on today and what we could improve and provide in the future. Concerning the replays, you will receive the replay of today in a few hours. You will be notified by email along with the certificate of attendance. So yeah, don't hesitate to take a look at your inbox. You will soon be notified when everything is available. So yeah, thanks again to everyone, and we'll see you in the next training. Training in September. Have a nice day. Bye.